Today we're going to focus on two-dimensional linear systems, constant coefficient ones. So we're going to write u, the vector function u of t is u given by a pair of scalar functions u of t, v of t, and think of this as a curve in the uv plane. And we're going to suppose we're given a differential equation of the form u prime is equal to a u of t. And here A is a constant 2 by 2 matrix. So it's not a function of t, it's just a constant matrix. A is A, B, C, D, like this. So let's just think for a moment about what this means. If you write it out, it says u prime and v prime is equal to this matrix A, B, C, D times uv. And so that is to say it's really the pair of equations u prime is equal to au plus bv and v prime is equal to cu plus dv. Okay, we've mentioned this kind of example before. And we're going to spend a fair amount of time talking about these examples because they really capture the behavior of a fairly general linear system. And we're going to talk about the sort of qualitative behavior of the solutions of these things. That is to say, draw pictures of what the solutions look like and discuss the asymptotics of the solutions, what happens as t goes to infinity and also t goes to minus infinity. And we're also going to talk about stability of these systems. I'm going to illustrate the notion of stability in each of these examples. So, by means of this example. So let's start with the simplest case. Let's suppose A has two distinct real eigenvalues. Okay, that's the simplest case. Then what happens? Well, so remember, this is sort of modeled on after you change basis. You can think of it as you can diagonalize A, and it just has lambda 1, lambda 2 on the diagonal. And we've seen it's easy to solve it once it's diagonalized. And I've essentially done this before. We saw that what happens is if you take the corresponding eigenvectors, then the general solution is u of t is equal to some constant c1 times e to the lambda 1 t times v1 plus c2 e to the lambda 2t v2. And that's the general solution. If you have a particular solution, you can solve it by solving an initial value problem. So let's just check that this really is a solution. So if you take u prime, let's see, when you take the derivative of this thing, the lambda 1 pulls down and the lambda 2 pulls down. So you get lambda 1 c1 e to the lambda 1 t times v1 plus lambda 2 c2 e to the lambda 2t. And I'm hoping that that's equal to a applied to u of t. So let's write that down. A applied to u of t is what? Well, let's see. C1 e to the lambda t is a constant, so you just pull that out and you get AV1 plus C2 e to the lambda 2t AV2. And now V1 is an eigenvector with eigenvalue lambda 1, so you get C1 e to the lambda 1t, and then here you get lambda 1 V1, and similarly here you get lambda 2 V2 because V2 is a lambda 2 eigenvector. And these two expressions on the right of the equal signs are equal, so u prime is equal to au. Okay, that's just an easy check that this really is a solution. So I'm going to illustrate these with a very basic example, which is where the matrix is already diagonal, or the eigenvectors are the standard basis vectors. So we take A to be the diagonal matrix lambda 1, lambda 2, and I'm going to illustrate three basic cases. The first one is where the eigenvalues are both positive, and another case is where one's positive and one's negative, and then a third case is where they're both negative, but they're always unequal. So lambda 1 is bigger than lambda 2. So let's look at the first, let's look at some of these examples. So the solution is going to be, as I said, e to the lambda 1 t times 1, 0, and then constant e to the lambda 2t times 0, 1. So let's graph these and see what it looks like. Well, let's take a case where lambda 1 and lambda 2 are both positive. So, for example, if you start here on the positive x-axis, then the solution just goes out to infinity along the x-axis. And similarly, if you're on the y-axis, or on the negative x-axis, you go out to infinity this way, and similarly here. So you're always going straight out to infinity along the axes. And what if you start somewhere not on an axis, like up here in the upper, in the first quadrant somewhere? Well, both terms are going to infinity, and the x direction is going to infinity faster, so you get a curve which looks like this. And the family of solutions looks like a bunch of curves like this. They go out to infinity as t goes to infinity, and the arrows, excuse me, you put the arrows on to illustrate it this way, and you get a whole family of these which looks something like this. And similarly, in the left quadrant, the curves all look something like this, and they're pointing with the arrows pointing out towards negative infinity. So as t goes to infinity, this u of t definitely goes to infinity, and as t goes to minus infinity, u of t is going to 0, 0. And this first infinity, I don't mean to say any specific direction, it's just going far away from the origin. So here's the picture again. And an important point to keep in mind is there's always the trivial solution, u of t is equal to 0, because that's a solution of u prime of t is equal to a of t. And that is to say, that's this red dot here where you just sit at the origin and you don't go anywhere. That is a solution to this equation. But this is unstable. This is an illustration of the notion of stability. And what it means is if you had that solution and then you perturbed it a little bit, suppose you moved the red dot just a little in any direction, it would get onto one of these other curves, and then it would go off to infinity. So that's an illustration of the notion of stability. Again, 0 itself is a solution, but if you jiggle it a little bit, it becomes something very different and goes off to infinity. And one way to think of this is you have an upside down bowl and you have a marble sitting on top of the bowl, and if you balance it just right, it will stay there. And in principle it could stay there forever, but in fact it's unstable, and the slightest motion, if you apply the slightest force to the ball, it will move a little bit, and then it'll just roll downhill. So that's what this origin being unstable is like in the differential equation. Okay, for the next case, let's look at the case where both lambda 1 and lambda 2 are negative, and again still unequal. Well, what happens is it's exactly the same picture, except that you change the direction of the arrows. So the solution looks like this. And the picture is, I draw exactly the same family of curves as last time, except now as t goes going to infinity, since lambda 1 is negative, e to the lambda 1t and e to the lambda 2t are going to 0. So the arrows are pointing in towards the origin. Okay, so drawing it again, it looks something like this, with the arrows pointing in. And now the stability has completely changed. If you had the solution at 0 and you perturbed it a little bit onto one of these other curves, it'll just flow right back down back to 0. So this is the opposite case to the previous one. The trivial solution is stable in this example. And one way to think of it is if there's this region, this green region here, if you just look at that region, you never leave it. If you perturb within that region, it stays inside that region. Okay, let's go on to the case when the eigenvalues are opposite signs. So let's see. The same solution, of course. Let's try and draw it. Now, something definitely different is going to be happening here because of the signs. If you look at the axes, on the x-axis, since lambda 1 is positive, the arrows are pointing out. But on the y-axis, since lambda 2 is negative, the arrows are pointing towards the origin. So what does that mean? Let's see. So how do we get the picture here? Well, what happens as t goes to infinity? Let's see. The second term is going to 0, and the first term is going to infinity. So that means that you're getting asymptotically closer to the x-axis like this. You're going off to infinity in the x direction, and the y coordinate is going to 0. So you have a bunch of curves which must be looking like this somehow. And if you think about it a little bit, think about what happens as t goes to minus infinity, you see that you get a family of curves which fit nicely like this. And notice that the arrows all sort of match up the right way. And over in this left-hand quadrant, they look like this, with the arrows pointing towards infinity in the negative x direction. All right, now the origin here is rather different than in the other pictures. There's a couple of, the arrows are sort of pointing in different directions, and this is called a saddle point. If you draw, I'll draw a picture another time which looks like a saddle. In any event, when the eigenvalues are opposite signs, it's called a saddle point, and this is again unstable because if you perturb it a little bit, you'll get onto one of these curves going off to infinity. Of course, you could possibly perturb it just to the y-axis, in which case it comes back, but that almost never happens. On every other curve, it goes off to infinity. All right. That takes care of all of the cases where the eigenvalues are real and distinct. That's actually not quite true. I haven't talked about the case when one of the eigenvalues is equal to 0, but let's not, maybe I'll come back to that. But at least if the, otherwise I've covered all of the distinct real eigenvalue cases. Another case which has distinct eigenvalues but is when they're complex. So let's look at that case. So that's where lambda is mu plus or minus IV. And of course v should not have an arrow over it. That's a mistake. U and v are real numbers. And let's look at an example. Let's suppose that A is the matrix AB minus BA. Let's see. What are the eigenvalues of this matrix? Let's see. Well, the characteristic equation is this, and that's this. And if you work it out, use the quadratic formula, you'll see that the answer is that the roots are lambda is equal to A plus or minus IB. That is to say that A is can be diagonalized to this complex matrix,
notice that it has trace 2a and determinant a squared minus b squared, a squared plus b squared. Anyway, let's see. Let's find the corresponding eigenvectors. Well, if lambda is a plus ib, it's easy to see that the corresponding eigenvector, v1, can be taken to be 1i. And so then taking the complex conjugate, you find that lambda 2 is a minus ib with v2 is equal to 1 minus I. Okay, and so that says that u of t is equal to c1 e to the a plus bi t plus c2 e to the a plus bi times t, 1 minus I. I forgot the t's in the exponents there. And that's perfectly fine, except it's not real. There's a bunch of complex numbers. There's a bunch of i's in there. So how do you get a real solution? Well, let's see. The thing to do is to write this out in its real and imaginary parts. I'm not going to give all the details of this, but e to the a plus or minus ib times t is e to the at, which is real, e to the plus or minus ibt, and then the second term is cosine bt plus or minus I sine of bt. And so that's the real, that gives you the real and imaginary parts of that term. And you see that u of t is equal to what? You get a c1, e to the at. I'll pull that out of the whole thing. And then I'll skip some steps. What you get is c1 plus c2 cosine bt and minus c1 minus c2 sine bt. And then you get a plus I, and you get something which looks similar with a sine and a cosine in it. And so you see I've pulled the e to the at out front and mixed up the other terms and the constants and the sines and cosines and so on. But now the point is you can take the real part separately. And if the real part and the imaginary part separately are solutions, and again, skipping a couple of steps, you find that the general solution, the general real solution, is of the form something times cosine minus sine plus another constant, again e to the at, times sine bt and cosine bt. So the point is there's this e to the at out front and some sines and cosines. So just to get the idea, let's suppose that d2 was 0, and then we would just have a constant times e to the at times cosine bt and sine bt. And notice that this vector here has length 1. Cosine squared plus sine squared is equal to 1. And so that's on a circle. And the radius of the circle depends on d. And if a was 0, for example, then you'd just be getting d times cosine of t and sine of t minus sine of t, and you just have a family of circles parameterized by d. And what happens if a is not 0? Well, for example, if a was positive, then as time goes by, the radius gets bigger and bigger. And so what you get is a spiral pointing outward. On the other hand, if a is negative, it's the same picture. It's a spiral, except now the arrow is pointing inward. Okay? So again, the eigenvalues tell the eigenvalues tell you the nature of the solution. The first guy here on the left is unstable because the arrow points out, and the other two guys are stable. And next time I'll talk about asymptotically stable versus stable and draw some other pictures.